So welcome to this video on adding phase-shifted sine and cosine waves and expressing the resultant voltage in the form of V equals R sine theta plus alpha. So it's a sine. This is a sine wave because it starts at the origin and goes up. Or is it? Because it could be a phase-shifted cosine wave. It could be lagging by 90 degrees or pi over 2 radians. This looks like a cos wave because it starts at 1 and then goes down, but it's possible that it is a leading sine wave that's leading by 90 degrees or pi over 2 radians. This one here, what could it be? Is it a sine or a cosine? And we're not quite sure. What do you think? It starts at 0.5 and goes up. And the answer is it's neither and it's both. It's a sine and a cosine, or it could be. It could be y equals sine omega t plus phi, or sine theta plus the phase difference. That could be true. Or it could be y equals cos theta plus the phase difference, or y equals cos omega t. They're both true, but for each case the phase difference would be different. So we're going to add some sine waves and cos waves together. V1 is 3 sine omega t plus pi over 4 radians. And because there's a phase shift, think of it as having a sine component and a cosine component and a phase shift of phi, which is pi over 4 radians on 45 degrees. And to find out the amplitude, we would square the sine component and square the cosine component, add them together, then square root using Pythagoras, and they would add up to 3. So the amplitude A is the hypotenuse, and that's 3 volts. But we can see it's 3 volts from what V1 says. It's 3 times the sine, so that means 3 is the amplitude. So when we add our sine waves and cos waves, we add the sine components together and the cosine components together, square them, add them, and square root them to find the resultant voltage. V2 is 2 cos omega t minus pi over 8 radians, which is 22.5 degrees. So it's lagging. And the same goes, because there's a phase shift, it'll have a sine component to it and it'll have a cosine component to it as well. And if we square them, add them, and then square root using Pythagoras, we'll find that the amplitude A is 2 volts. And using tan to the minus 1, the phase shift would be minus pi over 8. And when we add V1 and V2 together to get V3, what we're really doing is adding the sine components of V1 and V2 together and the cosine components of V1 and V2 together. Then we'll square them, add them, and square root them. And that will give us R, which is the resultant voltage of V3, because we want to express the resultant in the form of R sine theta plus alpha, or R sine omega t plus alpha, which is the engineering way. So let's look at V1 as a graph. It's a sine wave. It's leading because the phase difference is positive. And it has an amplitude of A volts. V2 in blue, it's a cosine and it's lagging. It's lagging behind the y-axis because phi is negative. And it also has an amplitude of A volts, whatever A is. And then V3 is the green one. It's the sum of the other two at any point. It's a sine wave and it's leading because the phase difference, what we call alpha, is positive because it's to the left of the y-axis. And the amplitude of V3 we call R. So we're going to find the resultant amplitude R and the resultant phase shift alpha for V3, which is the sum of the other two voltages. We could say R sine theta plus alpha, which is like a mathematical way of doing it, but engineers tend to say R sine omega t plus alpha. But theta and omega t are just the angle on the x-axis. So the steps to express in the form of R sine theta plus alpha. Step 1. Resolve each phase-shifted waveform into its sine and cosine components using a compound angle formula. And there's a few of these formulas. And it's worth saying that if your sine or cosine wave has no phase difference, or no phase shift, then it'll only be say a sine wave will only have a sine component, and a cosine without a phase shift will only have a cosine component. But if we have phase shifts in any wave, it'll have a sine and a cosine component. Step 2 is to use Pythagoras' theorem to find the resultant amplitude R for the third voltage V3, and then we use simple trigonometry to find the resultant phase shift using tan to the minus 1, and this is called alpha, and it's easy when you know how. So let's have a go. So know your formulae. Compound angle formulas, there's a few of them. We have V1 here is 3 sine omega t plus pi over 4 radians. And I'm going to use sine A plus B is sine A cos B plus cos A sine B. V2 is equal to 2 cos omega t minus pi over 8. So there's two compound angle formulas I could use. I'm going to use cos A plus B. But if I do, I need to make sure that my angle B is written as minus pi over 8 radians. I only like to use the positive versions of the compound angle formulas, so I only need to remember two. I could have used cos A minus B, in which case the angle B would be pi over 8, but the way it's just my preference that I like to use the positive version, so I'm using cos A plus B is cos A cos B minus sine A sine B, but I need to make sure that the angle B is always written and calculated as minus pi over 8, because A plus B is A plus minus pi over 8. So I'll use a compound angle formula for V1 to resolve it. V1 is 3 sine omega t plus pi over 4 radians. I'll use sine A plus B is sine A cos B plus cos A sine B. I'm going to let A be omega t, and angle B is pi over 4. So V1 is 3 lots of sine A cos B plus cos A sine B, and that's equal to 3 lots of sine omega t cos pi over 4 plus cos omega t sine pi over 4, which is equal to 3 lots of sine omega t times 0.707 plus cos omega t times 0.707. So don't forget to multiply out by the 3 in front of the brackets, and this becomes V1 is 2.121 sine omega t plus 2.121 cos omega t. So we've resolved it into sine and cos with no phase shift. And the same for V2. V2 is 2 cos omega t minus pi over 8 radians. I'm going to use, like I said earlier, cos A plus B is cos A cos B minus sine A sine B. I'll let A be omega t, but I must let B equal minus pi over 8 if I use this formula. So V2 is 2 lots of cos A cos B minus sine A sine B, which is equal to 2 lots of cos omega t times cos minus pi over 8 minus sine omega t times sine minus pi over 8, and watch out for the double negative on the right hand side. So V2 equals 2 lots of cos omega t times 0.9239 from our calculator minus sine omega t times minus 0.3827. And don't forget to multiply out by the 2, and this gives us V2 equals 0.7654 sine omega t plus 1.8478 cos omega t. So we've resolved V2 into its sine and cosine components with only one angle to manage now, omega t on the x-axis. We don't have to worry about the phase difference anymore. V3 is equal to the sum of the other two voltages. So we add the sine components and we add the cosine components and we combine the like terms. So V1 is 2.121 sine omega t plus 2.121 cos omega t. V2 is 0.765 sine omega t plus 1.848 cos omega t to 3 decimal places. And we add sine to sine and cos to cos. And this gives us V3, which is the sum of the other two voltages, is 2.886 sine omega t plus 3.969 cos omega t. And V3 is a resultant of the other two. So there's V3 with its sine and cosine components. So just think of V3 like the other two voltages. It has a sine component and a cosine component and a resultant amplitude, which is the hypotenuse. And we can work it out with Pythagoras. So what we do with Pythagoras, we square the sine component and square the cosine component, add them together and square root. And that tells us that the amplitude of V3, which we call R, is 4.9 volts. And then we use tan to the minus 1 of the opposite over the adjacent, which is tan to the minus 1 of the cosine component divided by the sine component. And that gives us the angle alpha for the resultant voltage V3. And that's 0.942 radians. And that's positive, so that means it's leading the y-axis. So to express V3 in the form of r sine theta plus alpha or r sine omega t plus or minus alpha, depending on the phase shift, we can do it now because it's equal to 4.9 times the sine of omega t plus 0.942 radians. Or you could say 4.9 sine theta plus 54 degrees. So we've done it and it hasn't been too painful. It's been pretty straightforward. So I've used Desmos to graph the three voltages. We have V1 in red, V2 in blue, and V3, the resultant, in green. So if I zoom in to look at the three waveforms, we can see V3 in green, and we can see the amplitude R is 4.9, which is what we calculated, and the phase shift alpha is 0.942 radians, leading the y-axis to the left. So we've got it correct. So the steps to express, just as a recap, resolve the phase-shifted waveforms into sine and cos components using the compound angle formula. And you only need to do this if they have a phase shift. Step 2, use Pythagoras theorem to find the resultant amplitude R for V3. And use simple trig tan to the minus 1 to find V3's phase shift alpha. So thanks for watching. Like and subscribe and look at the other videos at the top to understand more about omega and how to graph using Excel. All the best.